Ok, então agora eu vou começar a falar inglês. Hello everyone, good morning. I'm going to be the chair of this session. So first let's introduce the jury and then the participants. So about the jury, who can start?
Let's go. What?
Go ahead, Albert.
You can start, Albert.
Hello, I am Alberto Tufari. I am from USP EASH, also known as USP Leste. I work with education, with dynamical systems and optics. So good luck to everyone.
So, thank you, Alberto. Claudio, can you continue?
Yes, I'm Claudio Lenz Cesar. I am a professor at the Federal University of Rio de Janeiro, and I work with in the interplay between atomic physics and particle physics, working with antimatter, anti-atoms, and atoms, and molecules, and laser spectroscopy, and so on. Nice to be here.
Thank you, Claudio. Can you continue, Alexandre?
So good morning, my name is Alexandre Rocha. I'm a professor at Instituto de Física Teórica at Unesp, and I'm a computational physicist working on condensed matter and nanoscopic systems.
Thank you, Alexandre. Ian, can you continue?
Hello, everyone. I'm Ian. I'm doing my doctorate at UFABC. I'm working with stochastic process, studying evolution, and I wish you all a good fight today.
Okay, thank you, Ian. Ubirajara, can you finish?
Sure. Hello, everybody. I am Ubirajara Gero. Bira, I'm from UFMG. I work with biological physics. I hope we have a good fight today, also like was yesterday. Good luck for everybody.
Okay, thank you. So now about the teams. Unicamp can begin.
Of course. Good morning, everyone. I'm Leonardo Falabella, and I am with the Unicamp team right here. We are with Álvaro, Lucas, João Pedro, Gustavo, and as well as Adriano. I think I didn't forget anyone, right?
Okay, thank you. And now UFABC.
Hello, everyone. My name is Lucas, and I'm here with Rodrigo, Leonardo, and Vinicius. And we are the UFABC team.
Okay, thank you. So now let's start with the captain's fight. I'm going to share my screen. Everyone is seeing my screen? Okay.
Yes.
So about the time, is everything correct? Okay, I think it is. So first I will read the problem. So this is the physics fight of room 3A, and we are debating about the UFABC and Unicamp team, and this is the captain's fight. Okay, so now I'm going to read the problem. Colombian aguardiente. The Colombian aguardiente is a typical beverage in the country, similar to the Brazilian cachaça. When talking about this beverage, we can analyze both the nutritional facts and the calorific value in combustion. In Bucaramanga, there is a famous Teleréfico del Chicamoca, one of the touristic attractions. It has 39 cabins whose maximum capacity is 8 people. Now consider these cabins are operating in the whole track at maximum velocity with 8 people. Assume the downhill track has an inclination of 30 degrees with the horizontal direction. How many liters of aguardiente should be used as fuel to make all 39 cabins go uphill once. So I think now we can start the time. I'm going to let the screen to the Teams consult when it's necessary. Okay, so let's wait the 3 minutes. So the last 10 seconds, everybody. Okay, it finishes. So can UFABC team and Unicamp shows the results?
We show on camera or send the
In camera, please.
chat? Okay.
Okay, I need to. I think the camera is not showing right. Okay, 10 liters for UFABC team and
20,000 liters.
20,000 liters for Unicamp. Okay, so now I'm going to show the results. Okay, so the answer is 206.6 liters, and then UFABC team won. But first I will read the resolution. So the track's total extension is 0.3 kilometers, and the maximum speed is 6 meters per second, and an approximate weight of an empty cable car is at about 500 kilograms. If the total track is 6.3 kilometers long, the vertical displacement is h equal to 6.3 plus sine of 30 degrees, it's equal to 3.15 kilometers. So the work to carry the cabins on fuel is the work required to counterbalance the gravitational energy. The total gravitational energy is given by this expression, and then the result is 1.227 plus 10 to 9 joules. And then you can calculate the calorific value, which is 21.3 megajoules per liter, and then the amount of liters of alcohol we need is at about 59.9 liters, and then the equivalent aguardiente is at about 2006.6 liters, and then UFABC won. So UFABC can choose which is the position they want to begin.
We want to be reporter.
Okay, so reporter, and then Unicamp will challenge. So, okay, can the time begin with 1 minute? Okay. Okay, can Unicamp start your challenging?
We challenge UFABC on the problem sparkler.
Technical reject.
Okay, can continue.
We challenge UFABC on physics of math.
That's also a technical reject.
We challenge UFABC to present smashing spheres.
Technical reject.
We challenge UFABC to present LiDAR, electrostatic LiDAR.
Permanent reject.
Just to remember, Unicamp has already, UFABC has already done 3 rejections, so, and 1 permanent rejection. So now on, we will have 0.2 for decreasements in the grades, okay? Okay, so now we begin with the problems that it was presented by the opponent, opposed by the opponent, and then presented by the reporter, and finally verbally rejected by the reporter, okay? So Unicamp can, what were the problems that were presented by the opponent in the UFABC team in the previous fight?
Wait, just a second.
Isn't it the ones that Unicamp presented?
No, in the rules, the first that needs to be challenged is presented by the opponent, right?
Yeah, and the opponent is Unicamp.
Yeah, so the ones that we presented, right? Unicamp
Okay.
presented, because we are
Okay.
the opponent. So we presented Rising and Field Ball, Rising the Book, Field Ball, and I believe that's it, right? Yeah.
Okay, so UFABC.
So we challenge UFABC to present Rising the Book.
It's a technical reject.
We challenge UFABC to present problem Field Ball.
We accept the challenge.
Okay. So UFABC now has 5 minutes to prepare.
Mariana, can you allow me screen sharing, please?
Okay.
Thank you.
Sorry, it was Vinicius or Leonardo that asked it?
Leonardo.
Okay.
Pode ainda compartilhar.
Sorry, I'm a little bit confused. How can I do this? Go here. Okay. Okay, thank you.
Can you see my screen?
Yes.
Okay.
So when you want to start, you can.
I'll try to move to the next slide just to see if it's working. Can you confirm for me? I have passed. Can you see the other slide?
Yes, we can.
Okay, thank you. Okay, I'll start my presentation now.
Okay, can the time of 10 minutes begin?
Yeah, sure. I don't have a camera right now, so I'm sorry for that, but I'll present.
Okay, so now you can begin.
Okay. Hello, my name is Leonardo, and I'll present with Vinicius the problem number 4, called field ball. The problem states that a ping pong ball that has been partially filled with some fluid or sand will bounce much lower than a filled one. We will explain this phenomenon, and we will analyze the relevant parameters and with the height. We have used a paper called Rebound and Jet Formation of a Fluid Field Sphere on our theoretical approach of the problem. The image on left is the progression of a urethane sphere filled with 20% water dropped from a height of 10 centimeters. The circle on red shows the moment of greatest sphere deformation. In the first collision, we have an instability, which is the sloshing process. This collision is elastic. The circle on green shows the second impact, an inelastic collision, when the cavity collapses, forming a jet in the center. On image on the right, we have two images. The first one is the graph of the rebound trajectories of a sphere filled with different fluid volumes. On the second image, we have the trajectory of the ball, filled with 20% volume. Here we have, in the circle on red, we have the first collision, when the sloshing process begins. On the second moment, we can see the maximum height of the first rebound, and then we can see the jet, and in the third moment, in the circle on green, we can see the jet formation. The paper focuses on three parameters: ball material, viscosity, and fluid volume. The most important parameter is the fluid volume, at least in terms of rebound suppression. The graph on left shows how the variation of fluid volume affects the height of the rebounds. On right, we have four graphs that shows how the viscosity has a significant smaller effect on rebound suppression. Here we have spheres filled with different fluids and an empty sphere. We can see how the height of the rebounds are significantly lower.
The paper brought us a lot of information about this problem, and even was used to answer the questions. But it didn't analyze what happens when you have a ball filled with sand. And to analyze that and to confirm what the paper said, we make our own experiments. And to make those, we use a table, a ball, which will have a hole that we can use to fill it with water or sand, and a cell phone to record the bounces the ball will do in the table. A sample of the recording is right below, where you can see that when the ball bounces in the floor, we can clearly see in the audio it happening. And we then analyze these times between one bounce and other versus the number of bounces. You can go to the next slide, please. And with that, we made our own measurements. And first of all, we analyze what happened when we have balls filled with water. And we can see that what the paper brought us, that the full ball is the most similar to the empty, is brought in our measurement. We can see here the black one and the red one. Those are the most similar compared to the others. Yes, they are not very similar, but compared to 1 millimeter, 2, and 3, they are the most similar. And with that, we can confirm what the paper brought us. And with the graphic on the right side, we can analyze what happened when we have a ball filled with sand. In this one, we can see that what happens in the ball with water also happens in the one with sand. When you have a full ball, we have the most bounces. We have the thing that the most gets near with the empty ball. And we can also see that when we have a ball filled with 20 to 80%, we have something almost 100% inelastic, because it have just 1 or 2 bounces, then it stops bouncing. And you can go to the next slide, please. And to prove even more what happens, we even recorded a GIF. You can pass again. That shows what happens when I have a ball full of sand and how it moves. Just wait till it begin again. We drop the ball from a certain height. It goes in a linear way. It hits the floor and then it begins to go to the right and the left when we have this sloshing inside the ball. And it makes that what the paper brought us, the explanation, the paper. And it happens in the sand. Also, what that is like what happens in the water that brought the paper. You can go to the next slide. And then to conclude our presentation, we can see that the parameter that the most influence was the height was the volume of liquid. The paper brought us that the other parameters are not as relevant. And with our analysis, we also saw that the balls filled with 20 to 80% with sand are essentially inelastic. And the ball filled with 100% with sand present the most, the some elasticity and the most number of bounces. And that's it.
We can hear you, Mariana.
Sorry. So thank you, team of UFABC. And now we can start with the technical questions for the opponent team for the reporter. So 2 minutes for that.
So, hello, thank you for your presentation. My name is Alvaro and I'll be opposing for Unicamp. The first point I'd like to address is, could you come back to your slide where you show the sound of the ball? You did a sound analysis.
Yeah, sure. Hold on.
Well, in the meantime, I think you could answer, what is the relevance of that for the problem?
So basically, that's how we analyzed the problem. We have measured the sound of the bounces, and with that, we can measure the time interval between the bounces.
Did you measure the height of the bounce?
Yeah, the height. No,
you said you measured the time interval, but did you measure the height of each bounce?
No,
we didn't.
Do you think that's relevant?
I don't think so, because with the number of bounces, we can come to the same conclusion as if we have measured the height of each bounce.
Okay, we can discuss that further during our fight.
Yep.
Do you have any images of your setup? Like pictures?
We just have the GIF that we showed.
Okay.
But that's basically the representation that we did.
Okay. Could you come back to those graphs as well that you did?
Sure.
Do they have any uncertainties associated with them?
The uncertainty is irrelevant. It's almost 10 to the -6. So it wasn't even possible to put in this scale.
Yeah, the error bar would be much so small.
Yeah. Absolutely. Do you have any uncertainty in the height that you release the ball from? And do you think it's relevant?
Yeah, we do. We have showed in this previous slide here. Hold on.
Okay, so
we have showed here.
Okay.
Here you have the and Unicamp team. You can continue this discussion in the next session. So Unicamp can prepare the opponent presentation now.
Okay, I'll stop sharing my screen.
Okay, thank you.
Sim. We would like to request a tactile timeout.
Okay, so 1 minute.
Can I share my screen? I don't think I'm...
I think Henrique needs to do it.
Me. Oh, let me see. Can you see my screen?
Yes.
So I'll start my presentation.
Okay.
When
Gustavo,
the time.
can you begin the time?
Hello, everyone. My name is Álvaro Ribas, and I'll be representing the University of Campinas in my opposition of problem 4, field ball. So if we take a look at the problem statement again, a ping pong ball that has been partially filled with some fluid or sand will bounce much lower than a field line. First, explain this phenomenon, and then how does the height of the bounce depend on relevant parameters? We thank the presenter team for his report team for his presentation, and we would like to analyze what were the positive points and the points to improve on his presentation. On the positive side, we had a good review of literature. That was a good paper with good references. They identified the main parameters and the most important one, which is the filling of the ball. We agree with that most important parameter. He took experimental measurements with sand and audio analysis, which was really interesting. And he analyzed both the cases that were requested by the problem statement, which are with water and sand inside the ball. However, some points could be improved on his presentation. Mainly, the fact that he did not show images of his own experiments. I think that would have been a lot more clarifying. Especially for us to see how the ball was released. We think the release of the ball is a relevant parameter to the solution of the problem, and we would like to discuss that during our fight. Besides, he could clarify the sources of his uncertainties for the results, since he said they were so low. Besides that, from the video with the sand, we could see a sand outflow during the bounce, and we think that could be even in a smaller order of magnitude, relevant to the percentage of filling of the ball. That will generate an uncertainty and a difference in behavior of the ball. Furthermore, he did not show a graph of the height, which we think is really important to the solution of the problem, despite having measured the time between each bounce. A graph with the height as a function of time would have been really relevant. And finally, he did not analyze the first bounce as compared to the subsequent bounces for both materials. We believe that the first bounce differs from the second bounce and the bounces that follow. We'd like to see, we'd like the presenter team to explain how they think each filling of the ball, each material behaves as the number of bounce increases. So we have some points to discuss. First and foremost, how can you have a reliable control mechanism to release your ball? Secondly, where does elastic and inelastic collisions occur? You said that in a first moment, it is a elastic collision, if I'm not mistaken, but we would like to discuss that better. Third, what is the relevance of the sound of the ball? You talked about that during our technical questions. I would like to come back to that point. We would like to see the dependence of the height of the first bounce with respect to relevant parameters. And we'd like to ask, what is the relevance of viscosity? Since you mentioned the paper you consider relevant, considers it an important parameter. And finally, and most importantly, we would like to address a crucial point is that we think you did not analyze completely, you did not solve completely the problem statement because you did not analyze the height of the bounces. So that was my initial thoughts. Thank you. I'd like to invite the presenter to our fight now.
Okay, so we can start with the 5 minutes time. Okay, so let's begin.
So yeah, I can begin answering the questions. So about can you come back to the negative points?
Do you want me to share my screen? Yes.
You were already sharing, I think.
Okay.
Yeah. So about the uncertainties of the results, we basically have used a sample recorded between the
just before you start, could you share your screen, please? I'd like to see your presentation again.
Sure. Hold on. Just 1 second. Can you see it?
Yeah.
So basically, about the uncertainties of the graph, we have used it, as we have mentioned, we have used it, hold on. We have used the sample of the recorded sound for the bounces, right? Mm-hmm. So the sampling rate of the software was significant small. So between the peaks here, it's basically 5 milliseconds of interval. So, and okay. we are working with seconds of the unit of time interval. So the uncertainty would be would be small in comparison to the dots here. So it basically you wouldn't see the error bars.
Absolutely. Now I understand. Yeah, that's clear.
Yeah.
I'd like to see another point which I think is relevant. How is your release mechanism to the ball? Did you release it with your hand or not?
Yeah, we released it with our hand.
Do you think that's relevant to the problem?
It's basically a free fall.
Okay. Yeah, it's a little bit relevant because we can do a little spin to the ball and change a little bit, but we didn't find a better way to release it. And
okay, one of my suggestions is you could use a vacuum mechanism that when air starts to flow again, the ball would fall vertically and with no rotation. That will be relevant because we believe that rotation changes the height of the subsequent bounces. And mentioning that, did you measure your heights, your initial height and your subsequent heights?
So the initial
you do have that on the paper, right? If you come back to your first images.
Yeah. Yep, the paper brought us extended analysis about the height through the time, about the balls filled with water and other materials. We have already its analysis, and if you can see here in the sample, we can see that the avial has a high point. Whenever the bounces come, we can see that there are some higher than others. We can see that it begins to get little by little. It begins high, but then it gets lower. You can see.
But did you explain how one height depends on the other? On the previous one?
Yeah.
Is there a relationship between them?
Yeah. There is like some, depending on the height, you can see that the audio becomes louder or not. And if you, Leonardo, you can go to the 12th slide. We have some extra slide.
Okay.
Go there. Sorry, just a second.
Mhm.
You can go to the other one. The other one. We indeed analyzed a little bit about it, but we didn't brought the information because we didn't present the theoretical model. But we did indeed analyze the time of flight with the number of bounces, showing that we use a logarithmic scale, we
Okay.
can see something linear. We just didn't show a
Okay.
theoretical model, so we thought it
Uh,
wasn't able to be shown.
Yeah, basically.
absolutely.
Sorry,
Absolutely.
go ahead.
No, I just think a model would have been really relevant, especially because they asked for this
Yeah,
on
but
the problem statement.
yeah, but we
So
indeed answered
you
the
would have
problem in the paper.
you had
Sorry.
no, but I think would have been more productive of your solution for you to analyze and compare your own graphs with the graphs from the reference. You have very clear graphs that they show a relationship between height and time.
Yeah,
Okay.
but
And
go ahead, sorry to interrupt.
and I think you would have different
Sorry
uncertainties
for
that you could talk
interrupting,
about.
but
Okay.
now it's the 6 minutes time for the general discussion between the teams. Now every members can participate.
Yeah, I'd like to ask.
Can I join really quickly just to clarify one point?
Yeah.
Okay, so you asked about the heights of the graph. If we
Absolutely.
had data on the heights, and the reason why we measure the sound interval between the bounces is to measure height, because we can plug it into accelerated motion equation and figure out the heights. We don't have a graph of it, but that's how we analyze the heights.
Okay, I think that would have been relevant to your solution. Furthermore, do you think the rotation of the ball is relevant to this height? How can you know that a non-rotating ball will have different heights? If a ball falls rolling, it will not bounce like a ball that is not rolling.
The paper, they have done a really controlled experimental setup, and the ball wasn't rotating on the paper, and you can see on the graphs. Just 1 second, let me.
Okay, but I believe
you can see on the graph that there is in fact a rebound suppression, and the height is getting slower in each bounce. So yeah, indeed, a non-rotating ball, the height gets slower in each rebound. And can I make a quick comment?
I'd like to ask Leonardo to make a quick. He has raised his hand, so I think he would like to add something.
Yeah, thank you, Alvaro. I think that the graph and analyzing the heights was like the key point of the problem, and because this gives a really base understanding of what is the main important mechanism of energy loss on this problem. So I would like to ask you, what do you think is this mechanism?
Can you say the question again, please?
What do you consider the main mechanism of energy loss on this problem?
Basically, hold on, I'll come back to the graphs, our measurements. So basically, we can see that when we have the ball partially filled, the number of bounces are smaller than the other ones, right? So that's when we have, so the most significant inelastic collisions happen when the ball is partially filled with the
I see.
volume.
Your graph is clear on that. However, what is the main mechanism that causes this difference? Physical mechanism.
It's basically the energy loss in each collision.
Okay, but what causes the energy loss?
Leonardo, please let me talk. As you mentioned on the, as he mentioned on the presentation, it's the sloshing mechanism, right? When the water inside of the ball shows some instabilities. On the second bounce, you have that jet formation that gathers the momentum of the ball. So instead of an elastic collision, you have an inelastic collision because the most of the energy is dissipated into that jet formation.
Oh yeah,
okay.
That was the point of my question. We agree with you.
And
sorry, I didn't understand at first your question.
And do you think that transfer of energy mechanism is different from, for example, for different materials, if you have a ball filled with water or sand, or as you mentioned, a very viscous material such as honey or glycerin. Do you think it is the same mechanism, and what is the order that changing parameters such as viscosity will affect this change of energy?
Yeah, I definitely believe that the mechanism is still the same, but there will be very different energy transfer for different viscosities, right? So if you picture some liquid like honey that has a very low viscosity, you wouldn't get a big enough jet formation, so you would lose less energy, right? Yeah. So definitely is an interesting parameter.
Okay, I think it would have been really productive if you pointed out those parameters at the beginning of your presentation. Does someone have a mic problem?
Lucas.
Can you hear me? Yeah, okay. So I think we do agree that the main mechanism of loss of energy is turbulence due to the splashing of water inside the ball. And within respect of the parameters, the physical parameters of the liquids, the fluid inside the ball, what do you think is more important, the density or the viscosity of the fluid? Please.
Yeah, density or viscosity, what is more important?
Well, I guess both have important aspects for the sloshing mechanism, right?
Yeah.
If you have a high density material with very high viscosity, I guess that would be the greatest energy loss possible, right?
Okay.
I don't know.
Overall, I think it would have been more productive for your solution if, for example, during your presentation, you showed how those different parameters were varied during your experiment. For example, different material of the filling, the changing material of the ball that you mentioned the paper considers to be important. And if you
the initial height of the falling ball as well.
Absolutely. I think those parameters, those points would improve your presentation, and would like to see them. But thank you anyways.
Thank you, Unicamp. Thank you, UFABC. Now the final points for the reporter team.
I would say that our result, at least with water, have agreed with the paper that when the ball is partially filled with fluid volume, it has the most inelastic collisions, and therefore the number of bounces is smaller. And I think that the main new result that we brought here is that the ball 100% filled with sand presents some elasticity because the number of bounces is bigger than the other one. So I think that would be the main result of our presentation.
Okay, thank you. Now the questions from the jury.
Can I stop screen sharing?
Yes, of course. Claudia, you can begin.
Okay, well, thank you very much. Very nice. The presenter team showed the sound analysis, and eventually you showed the time of flight in the discussion. I think that was very important to be there since the beginning. The time of flight can be turned into a height, right? So my question is, why didn't you made a plot of the height with that? And second of all, a question for both teams. Would the time of flight be turned into a height represent the center of mass movement or not? That's a question for both teams, okay? So first, a question for the presenter. Why didn't you turn the time of flight into a height analysis? And second, if you do that, is that a representation of the center of mass movement or not for both teams?
The paper indeed brought us very deep analysis about the height and the volumes and the different types of liquids. So we thought that analyzing other parameters would be a more important thing because the paper had analyzed those. And to answer the question about the center of mass, the sloshing could really answer it. Indeed, there are some photos that we can make with the figure that we can see that depending on the view. Sorry, can we present just a slide to show it? Yeah, Leonardo, can you? I'm gonna try to present. Sorry.
Just in the
Okay.
meantime, I'd like to point out that we do not think that the tracking of the height represents the center of mass because of the sloshing
11.
mechanism.
I'm
Slide 11.
sharing. Which slide do you want, Vinicius?
11.
Okay, hold on.
The other one. The other one. Yep, this one. This. When we have this is a figure that the paper brought us about the center of mass during the time, and we can see that depending on the time, the height, we can see that center of mass is in a different position. It is different because of the sloshing process. So we think it's important to analyze too.
Yeah, just completing my answer, I think rotation it is also relevant because of, as a result of the sloshing process or of the release process. And for example, for very viscous liquids such as honey, you have you see that the honey does not move within the time of bounce. So it changes its position over time. And again, the center of mass is really unclear in these situations as well, even if you do not have a clear sloshing such as water.
Very good answers from both teams. And indeed, even with a video, you could also not determine the center of mass unless you had a very high resolution system in 3D or many videos with a transparent ball. Okay, thanks.
Okay,
Thank
any other jury wants to comment?
Can I go? Yeah, sure. First, about the error. So you measure the sound, and the sound starts high when I believe when the ball is reaching the floor. I don't know what was that. But then how long it takes to bounce to get up again. You just get the first moment, or you have with the sound a measure of like an error of the time of that the ball stays in that situation, smashing the floor for the presenter team.
So we can you ask the question again, please?
Sure. Sorry, I think I was a little bit confused. Right. So the sound, the sample of the sound is very small, so you have a very small error. But how long it takes? How long is the time of the sound? And if that time of the sound is the time that the ball is in the contact with the floor?
You mean the duration of the sound bounce?
Yeah. Can you talk about it? I think that's an error that you are getting from your measurement that I think was very ingenious, very nice.
So you are talking about how long the ball bounces on the floor, right? Or you mean the time interval between the bounces?
No, how long it takes bouncing in the contact with the floor.
Yeah, we didn't analyze that. We just analyze when the ball hits the floor, and then we have a peak. But we basically analyze the time interval between the bounces. And I to be honest, I don't think there is a relevant error in the time that the ball bounces on the floor.
Okay. One question for both teams is that this measure is very good for many bounces, but with the ball partially filled, I saw that you have just one bounce or something like that. It's a good method to analyze this case. What you can do better, I don't know. What are the thoughts you have in this partial? So I think I took a lot of time, sorry, but go ahead if you can both comment on that.
Yeah, so I think a more interesting method, again, would be to track the position of the ball over time. Because if you have those images on a tracker, you can see that although you have very close bounces, I think it's what happens when you have a half-filled ball. Those bounces, the difference between the height of the first bounce and the second will be clearer if you had the position. Because if you only have the sound, they're going to be so close to each other that it's going to be harder to tell each one apart. So I think a tracking method would be better. And you also have some uncertainties associated with it that are, I think, clearer to calculate.
I think that the advantage of the sound method is that we can analyze a bigger number of bounces. Because, for example, when you are tracking, sometimes when the height of the rebounds are too small, it's hard to analyze this, you know. So we can have more data of the bounce, at least the number of bounces when we are analyzing the sound.
Okay, thank you.
Okay, so one last question from Alberto.
Hi. What are, my question is to the reporter team. What are the reasons that that make you to use the sound wrapper, not the image? What are the reasons?
As said before, the paper already analyzed about the images. It has a very deep analysis, and we try to analyze the number of bounces to have a different analyzing to analyze the movement to more bounces. Because in the camera, for example, in the GIF that we showed, we can analyze the first, the second, and the third one. We already it's not in the camera in the video. So when we analyze the audio, we can hear more, we can see more bounces, we can analyze more bounces.
We can have more data, so our analysis is more precise.
Thank you for your answer. No more answers for me.
You're welcome.
Okay.
No more questions.
So 1 minute for the jury to decide the notes. Oh, okay. So now, first let me see. Okay. I'm going to say the grades from the reporter team and then for the opponent team. So for the reporter team, from Alberto is 10. From Alexandre Rocha is 7. From Claudio Lenz is 6. From Birajara is 6. And from Ian is 5. Now, for the opponent team, the grade from Alberto is 9. The grade from Alexandre is 8. From Claudio is 9. From Ubirajara is 7. And finally, from Ian is 7. Okay, so now we have the comments from the jury.
Okay. I think I gave one of the lowest grades for the reporter team. I thought it was very ingenious way to get the bounce with the sound, and I thought that was very nice. But just to use one peak was then you lost all the information you could get on that. If you get the structure of the bounce, you could get information for the other bounces. That would be very nice. And even from the opposing team, I think they could see the merits of the way the other team did the thing. So were just asking about the height, and that was one problem for their reporting. They should have put the height of the center of mass, and that's it, right? But then the method was very nice, but you should address the problems of that method, and I think you did not did that, right? So that was my grades, was like that. Okay. Why?
Claudio, you can continue.
Okay, well, I think it was very ingenious, very nice to see this sound, but I think the team from UFABC, just because the video analysis was done in the paper, they thought they would not have to redo it, and I disagree with that. I think you should really have both methods are complementary and very nice. So you should have done as well a video analysis, okay, and measuring the height. And you had the information of the time of flight, so you could have turned that into a height analysis as well, okay? And the other thing is that seeing the sand go out of the ball, I mean, maybe it would have been nice to just put a little bit of glue on that hole, on your syringe hole, and avoid anything going out, because you get extra torques and things like that. But it's a very nice kind of measurement, and there's more that you could explore with sound. So congratulations, and I think the opponent team got to the main points, so that's why I had this difference. Thank you.
I would like just to compliment, but I think I totally agree with Claudia and with Peter. You had a very ingenious way to track the bounces with the sound, but you have just that. So if you had comparing this analysis with the bounces in the tracking analysis would be a very great work. So that's why I give my lowest grade. And I'm sorry, it's congratulations, but I just think it.
Well, can I talk now?
Yes, of course.
First of all, congratulations to both teams for this discussion, and I think that UFABC team improved the science about the subject. They show a new way to do that. It's very important, and based on the points that sent to me to do the scores for you, I said that you are brilliant. And when you are asked about the height, you presented a plot that you have not presented. So I guess that it was very that impressed me a lot. I guess that the Unicamp team has a problem when they are surprised. They were very aggressive, in my opinion. So that's the reason that I remove one point of view, and I suggest if you are going to another place, don't do this behavior. It's very bad. Don't interrupt people when they are talking. I don't like this. So you are very aggressive. So this is the reason that I give these points, and And I based it not, I do not consider you a best physicist in the world. You are not. You are students, you have a lot of things to do. So try to understand the flaw of the others. The most things I'm telling this, don't try to be so competitive. I know that's the game, but do not use this kind of thing to destroy others or to show that you are right and the other is wrong. I know many of my colleagues like to do that. I don't agree with this behavior. So that's my comment. Thank you.
Okay, so thank you everyone. Now we are going to do a 10 minutes break and we go back later. Okay. I will stop.
Recording stopped.
Alguém tá por aí?
Eu tô.
Não, tranquilo, é que eu só tinha feito um comentário lá no chat sobre a pergunta do Cláudio, a observação do Cláudio, e era só isso mesmo.
I don't know if everyone is here, but I would just like to make a quick comment on what Alberto touched on his comment. If we transposed a little aggressive or something like that, we're completely sorry. This is not our intention. We completely respect UFABC and all other teams on the competition. It's really hard to guide this discussion to where you want them to go, and even on this distance calling, we have the latency of the connection, which make it even harder. So if we were aggressive again, we are completely sorry. And I just want to be clear that we just want to learn some physics together and discuss and learn from each other. So again, we're completely sorry if we transpose something like that.
Yeah, Leonardo, thank you for mentioning, but don't worry about it. We did not feel personally attacked or anything. We know that it's the game, right?
Yeah.
So don't worry about it. Yeah.
Yeah, it's the game, but try to listen to your opponent with give him space to talk to. I also felt that you interrupted the other team. You team, like, it's a competition. You guys are excited. I know you are. So, but just try to listen to your opponent and keep going. You guys are doing a very good job, both teams, and we have also to learn this thing. We are learning physics and also how to approach the other team in this competition also.
Yeah, we really appreciate the comments. We will try to be more respectful.
Okay.
Yeah, Leonardo, I would like to say the same. In fact, I think that you had made the best opposings of the competitions now, but you have, if you were, more, polite and friendly, you have gained a grade even better for me. All of them.
Oh, of course. Thank you.
Okay, everyone is here. Unicamp team, it's complete.
Can you hear me?
Yes.
Okay.
UFABC team, is everyone here?
Yes, everyone's here.
Yeah, Unicamp is complete here.
Okay, and about the jury, is everyone here? Okay. So let's start now. UFABC team challenges Unicamp. Oh, I need to start the recording.
Recording in progress.
Okay, now we can start.
Okay, the first problem, let me just enable my camera. The first problem we'll like to challenge Team Unicamp is problem number 11, smashing spheres.
That's a tactical rejection.
Okay, I would then like to challenge number 2, air bounce.
Tactical rejection.
All right. Then number 9, electrostatic lighter.
Permanent rejection.
Okay. Then number 10, droplet sandy fingerprints.
We accept the challenge.
Okay.
So now it's 5 minutes for the reporter team prepare.
The reporter for Unicamp will be João Pedro Minquilo.
Can you all see my screen?
Yes, we can.
Okay.
Okay, can you start?
Yes. Hello, I'm João Pedro Minquilo, and with Leonardo Falabella, we're going to present the problem 10, droplets and the fingerprints. The problem statement asks us, when droplets fall on a surface covered by a layer of sand, interesting patterns are formed. Study the formation process. What parameters of the droplets can be inferred from the resulting pattern? So we're first starting to analyzing the phenomena and what happens with them. These are images that we take from our own results and the own experiments. We can see that the different craters are formed using different sands. We tested it with 3 types of sand: a fine-grained sand, a medium-grained sand, and with beach sand. First of all, we start to analyzing the crater or origin and how the phenomena occurs and they are formed. The origin of the crater is due to some behaviors of the sand, that is, it behaves as solid-like and fluid-like. Both droplet and granular bed suffer deformation, and the liquid of the droplet mix with the grains. And the results of this phenomena of the problem results in the craters, different craters, as you can see in the image. We can divide the crater formation in 2 phases. First is the droplet impact will cause the sand spreads, is due to grains that form an external crater, and this occurs due to the deformation of the sand layer. We formed a ring of dry sand, and it is similar to a solid impacting on a granular substrate. Now we can talk about the droplet impact that results as the droplet spreads. The droplet first spreads and after retracts. When droplet is in contact with the sand, the water and the grains mixing, and this results the internal crater, if it is the wet crater inside of the external crater of the dry sand. So we can talk about what determines the difference in crater diameters and formats. And as you can see in the image, we have different formats of the craters, and it is made for the same sand. We can explain this dividing the process of the crater formation in 2 stages: the spreading and the absorption. The spreading is the spreading of the sand and the water, and it ends, the spreading of the water ends when the droplet reaches its maximum diameter. It is assumed and is very proximal as the external diameter. And the absorption is the droplet starts to retract, and at the same time, the sand is imbibed by water, and the liquid will stop, resulting in the wet crater. It's the internal crater. So this process to stop the crater, the wet crater, is due to a competition between this process, the droplet spreading and the water-sand mixture. It's the imbibition of the sand by water. So we can show a few the equations of the tau spread. It is the time, characteristic time of the droplet spreading, and the imbibition time, that is tau imb, that is give us the time of the imbibition process. And you can show you three situations that is different, and the craters illustrate that. The first image, as the left, occurs when the imbibition time is smaller than spreading time. So the droplet drops, the drop impacts on sand and form a planar crater. It's not exactly a crater, it's just the position of the water. The second image, the retraction time is the droplet spreads and it retracts. And the retraction time is bigger than the third case. That is when the retraction time is very small, and the internal crater
almost don't retract. It's the diameter of the internal crater is almost the diameter of the external crater of the sand. So we can model the crater formation due to and its relations with some parameters. First, we have the droplet parameters, that is the diameter, impact speed, surface tension, density, and viscosity. And the first 4 parameters we can use to introduce the Weber number. That depends on if it's 4 parameters. And the sand parameters, that is granulometry, packing fraction, it is related to the compaction, wettability, and the permeability. These all parameters would reflects and will cause different effects for the internal and external crater diameters, affects the crater format, the arrangement of the liquid in the sand, and the energy distribution, that is the energy used for the droplet formation plus the energy absorbed by substrate that causes the sand deformation. Let us introduce you our experimental setup. We use 2 experimental setups that is very similar. We're using the droplet source as a syringe and the landing surface to add the sand, glass plate or acrylic plate. And the interest that we used the landing plate, and we used coins to measure the sand thickness, to control the sand thickness. We had 4 coins in the border of the plate, and we added other plating up this plate up the coins to level the sand with the sand thickness with the thickness of the coin. So we could vary this and control this parameter. And with the syringe, we could control the height of the droplet release. So first of all, we can start to analyzing the results and how the craters how with the craters we can infer some parameters of the droplets. So we can first analyze the influence of outlet diameter, and we do this varying the droplet diameter using syringes with 2 different configurations, one using a needle and the other one without a needle. As you can see the diameter of the both of them, and we can see the difference in the crater diameters, the final crater diameters using 2 configurations. And this we can infer first of all that the reason for the difference is the diameter of the origin droplet. Second, we can proposing a Weber number ruler. We can do that if we analyzing experiments varying the height and varying the impact speed of the droplets, consequently varying the Weber number. We can do this for both types of sand we use in our experiments. And if we have this, we can just looking at crater for the first time without knowing anything. It's possible to estimate the Weber number of the droplet that impacts with this Weber number ruler, and knowing some parameters of the droplets such as density, surface tension, and the droplet diameter, we can obtain another unknown parameter of the droplets. So with 3 parameters, we can obtain the other one. We can show this for you in this graphic that we related the Weber number with the spreading factor, that is the diameter of the external crater over the diameter of the droplet. And we can fit it was well fitted of a line of slope 0.16, that was approximately 1/6, and we can show you the spreading factor is well fitted with Weber number power the 1/6. And with that, we can show you that the arrangement the equation of the droplet of the spreading fraction, the spreading factor, and we show you that the diameter of max is related to the diameter of the droplet. And knowing some parameters of the droplet, we can show you with a given random crater, do we measure the diameter of the crater, and knowing some parameters such as density, surface tension, velocity, we can obtain the droplet diameter. And with all using other parameters, we can know velocity or surface tension. And we know this factor n that is in interval 1/4, and the 1/6 from our experiment was 1/6, and for the literature we obtained 1/4 and 1/5. So we conclusion with auxiliary experiments. And without auxiliary experiments, we can estimate it with using the parameters, and we can estimate the droplet diameter. And with auxiliary experiments, we can infer other parameters of the droplet. So a general conclusion, the craters formation process and its main mechanism were explained, relevant parameters of the phenomenon were identified, experimental data were collected.
Thank you, Unicamp. Sorry for interrupting.
No problem.
But now we have the technical questions for the reporter team.
Could you go back to slide number 5, please?
Yeah, sure.
How are the sand characteristics determined? The millimeter of each sand and each grains.
The millimeter of the grains.
Yeah, you mentioned that. Yeah. You give us like between 0.5 millimeters and 0.4 millimeters.
This size of the grains we obtained, it's a standard pattern for construction sand. We just know that, and we infer the diameter of the sand.
Yeah. And did you guarantee the uniformity of the sand for all your experiments? Because when you press it, it changes depending if you press it or not, right? The packing of the sand changes.
Oh, we guarantee in our experiments compacting the sand. We can obtain a very similar sand for our experiments. We compacted it, and because of that, we can guarantee it.
Okay. Did you consider statistical error to generate your error bars, or was it just from each measurement?
Here, we calculated the uncertainties for it.
Considering the instrument uncertainty, correct?
Yeah, considering the instrumental uncertainty. Yes.
All right. Yeah.
And the measurement of the syringe diameter that we did.
Yeah. Lastly, how did you measure the Weber number?
I measured the Weber number with the parameters of the water, surface tension, diameter of the droplets that we.
Yeah, we actually calculated the Weber number from this formula.
Yeah, we calculate using the parameters and the velocity obtained with the energy kinetic energy.
Okay, thank you. Now we have 3 minutes for the opponent preparation.
We would like a technical timeout, please. It's me, Rodrigo. Can you guys see my screen?
Yes.
Yeah.
So can you start?
Let me. Yeah. Okay. So hello everyone. My name is Rodrigo. First of all, sorry I'm not. Don't have my webcam. It stopped working for some reason. And I would like to thank João Pedro and Leonardo and the team of Unicamp for the very nice presentation. So let's dive right into it. So first of all, some positive aspects of the presentation. They did explain fully the mechanism that creates the crater and the pattern that is formed afterwards. They showed us some beautiful images and the GIFs regarding their experimental setup and how they measured it. They did a very nice theory considering the Weber number, which was interesting to see how that power law was formed. And it was interesting also to see how you managed to change the experimental parameters in a controlled fashion. So first of all, let's talk about some lacking aspects as well. I found that only one measurement for each Weber number is not sufficient. You should have considered uniformity on the sand as well as uniformity on the droplet. So it would require very different measurements. It was not clear to me how the thickness that you did change in your results, how the thickness changed the crater form later. You did not show that explicitly in the presentation. Also, it was not clear to me how you determine the diameter of the crater. Did you use the outer diameter of the crater, or did you use the residue that it formed afterwards? Because we know that you show the residue retracts after the crater is first formed. So these are two different things to analyze. It was not clear to me which one you used, or if you only fitted like a single line to measure the diameter, or if you fitted a circle. It was not very clear to me. Later, you mentioned a lot of parameters for us, but you did not explicitly say how they affect. You only studied the Weber number dependence, right? And the velocity that you used in the Weber number was only calculated through the kinetic energy, and I think that you should have maybe used another method because the air drag should be of a very important influence here. So some interesting topics that I think that we would enrich the discussion is firstly, how does the sand thickness changes the crater? Because there is a dependency, right? But in the literature, it's not very clear yet. And I also want to ask you, why is the Weber number power law that you found that was 1.4, if I'm not mistaken, or 1.6, why is it different than the literature's report? Also, you mentioned the surface tension and the viscosity as important parameters, but you only studied the surface tension in the Weber number dependence. But how is the viscosity and the Reynolds number important for your results? Because the surface tension is important, but the viscosity clearly has some factors as well. And what happens if you use different liquids with different viscosities and surface tensions as well. And you mentioned that the sand and the grains change the crater formation as well, but you did not explicitly said so. So I would like to talk to you about it as well. So if we can open up for the discussion.
Right, sure. If you want, I can share my screen.
Yeah, for sure. Okay. Stop sharing. Yeah.
Thank you for your presentation, opponent team. It was very interesting points that we can discuss here. First of all, you talked about sand uniformities, the different in the sand, right?
Yeah.
For this fine-grained sand, it is not very full of uniformities. It's very thin and very clear, very uniform. And for this medium-grained side sand, it has more disuniformities than the fine-grained sand. But our experimental setup can control this very well because the top of the layer of the sand is very uniform. The different grains can disappear, and it don't affect very well too much our experiment.
Yeah, but if you press on top of a sand, the center of where the sand is would have a higher packing compared to the outer layers, right?
No, I think you're not correct, because we did this for the whole plate. We added the coins in the borders of the plate.
All right, so let's jump to the discussion topics. How do you think the sand thickness changes the crater formed up
the
later?
Sand thickness changed the format of the craters, and if you remember, the problem statement shows this picture, and this is very different than the pictures that I showed you before. But we could reproduce this using a very thin layer of sand. You use, I think, just one coin, very thickness, very low thickness of the coin, and we can reproduce this pattern. But increasing the thickness of the coin and increasing the thickness of the sand, these pattern were not reproduced, and we did add. We varied for 10 different thickness of the sand, and the higher thickness we didn't observe any difference or any clear difference in the sand.
Yeah. I think it would be interesting to show how it changed, because in that picture you're showing us, we can see that the residue afterwards, it's not even there, right? We can see the bottom, and clearly, I think that having a solid bottom below the sand layer would change the crater, right? It's a very impactful difference between a deep layer of sand and a very thin layer of sand. So I think that would be a very interesting topic to discuss, right? To present for future.
I think it's it can be more explored, but we could infer for more thickness of the sand, the higher thickness of the sand, the difference is not very important. We couldn't see this very well.
Yeah, they are very clear two regimes, right? With a very thin layer of sand, is this the pattern that you look, and after you have a bulky sand, you have other patterns, as you said.
Yeah, maybe we can talk a little bit later, because we have some results showing otherwise, that for a very thin layer, the crater increases significantly. So it should be.
Oh, sorry.
But it's never mind. Let's jump to the point on the viscosity of the liquid, right? You mentioned that there's a dependence on several parameters, but I think you didn't explicitly show us how that depends. So you consider the Weber number for your model, but how does the viscosity and maybe the Reynolds number depends on the final crater result?
I think there is it can affect the experiment and the resulting crater, and we can show you this formulation at the time of the imbibition will be different with the viscosity, that is the eta here. But in our experiments, we didn't explore too much we didn't explore the variation of the viscosity, but it is a known relation, right? But the Weber number has all of the other parameters that we could vary in our experiment.
Okay, yeah. And for different types of sand, the results you showed us on your experiments were only for the very fine sand, correct? Or did you use
this
several?
is for very fine sand, and this is for medium fine sand. Medium.
And that plot you showed us, is that for all different? Yeah, this one. Is it for all
this
different types of sand?
This one.
Sorry for interrupting, but now the discussion is open for all the team.
Yeah.
Okay, this graph we obtained for the very thin sand, because we varied the high, and it is very clean, very clear the difference here, and we could measure very well the diameters. You said that we obtained the factor, and
you mentioned that the factor
6, right?
Yeah, exactly. Yeah. You mentioned that the literature reported 1/4. Do you know why you have a difference? Yeah.
Yeah, I know. This is due to our grains, and in the literature they use the smaller grains than I used here. They use the smaller grains, and one of the papers use the liquid with lower surface tension, and because of that they obtain the higher factor, and we obtain this factor.
Yeah, I was also gonna ask you if you could reproduce the analysis you did for this type of sand for all other sands, and see if the power law changes depending on the sand you use.
Yeah, because it's a reproducible experiment. If you do very different heights, as I said here, with auxiliary experiments, you can do different experiments, varying the height of the release of the droplet, varying the velocity, varying the Weber number, and we can reproduce this exactly graph and obtain the factor for the sand. But it's difficult. It's a trouble in the. It's a difficulty in the problem, because we have varying the sand, and we tried to do that, and we obtain this. But if you have a unknown sand, you can do this and obtain this and obtain parameters with this relation, right?
Yeah. And regarding the height, what are the heights you used to measure the how was the range that you changed?
I went from approximately 20 centimeters to 102 centimeters.
Okay. Yeah.
And I tried a very high altitude, high here in 190, and obtain a very different crater, right?
Why is that crater so different? That was an interesting picture.
Oh yeah, because this the velocity is very high, and the spreading of the sand is very disuniform because of that.
Yeah. It would be nice to know that the residue and the formation afterwards depends on the height. Then you didn't show us that in your presentation, right?
I did. I showed here because I increased the height of the release droplet here, and because of that I increased the Weber number. It's all from different heights of release droplets.
Yeah, of course. But that picture you showed us later has a very different shape, right? It doesn't even feel like a crater. It just seems like a wet sand. Yeah.
It's like we have a critical value for the maximum height that you can drop let a droplet fall and to create a crater, as the problem statement says, right?
Yeah. Here, near the 1,1300 of the Weber number, the crater almost different the shape, and increasing this, we cannot analyze very well the crater. And I stopped here. I know that is a extreme value, and I did a more extreme value here just to show us the difference, but I cannot analyze very well this for the relations that I found here.
I would like to ask you regarding the paper you showed. You showed us a GIF from the literature, right? And the residue afterwards, it forms like a circular sphere, right? Not this one, the one before. Yeah.
This.
I think that one. Yeah.
Oh, so, the rebound of the droplets.
Not only the rebound, but the sphere that the liquid forms afterwards, right? You have a residue that you did not show in your presentation, right? It's not like a crater. It's the liquid gathers and retracts and forms like a little ball right in the middle. And so why do they have this behavior on the article, but you did not observe it?
Oh, I cannot observe this. I know what you're talking about. It's more a sphere of the droplets.
Exactly, yeah.
And I didn't obtain this formed for our sand, for our experiments. I think the reason is the granulometer of the sand.
Yeah, I believe that the reason is that you used very high heights, right? You start with 20 centimeters, and I think with a lower centimeter distance in lower energies, you would get this result.
No,
because the article says that the granular residue afterwards depends on the energy scale, right? And the sphere can only be reached when you use lower energies, right?
Yeah, I agree with you that this pattern of formation with a sphere is obtained for low highs of the low highs of droplet release and low velocities. But I'm sorry, I need to retract me because I showed here, and I did for lower highs too. Actually, this image we obtained for 6 centimeters, and I just showed these highs because I started my graph with this high because for lower high, I didn't obtain very well a crater. It's just a deposition of water, and this is a result for our low high, and not a truffle, as you said, a sphere.
All right.
Thank you for the both teams. Now the final punctuations for the reporter team.
So I would like to congrats the opponent team and thank you for the discussion. I think we could reproduce very well the experiment and reproduce very well the crater formation. We did our own experiments and obtained very good data. We could completely solve the problem statement. That is, we explained the crater's formation process, and we proposed a way to infer parameters of the droplet from the resulting crater. Even if the sand and the parameters of the droplet, parameters of the sand is unknown, we can obtain or estimate some parameters of the droplets that we can infer from the resulting crater. I think is that. Thank you for your attention, and thank you, opponent team.
Okay. Now 6 minutes for the questions for the jury. Yeah, you can start.
I have a question for the reporting team. You are saying that the power law that the Weber numbers follows is between 1/4 or 1/4 and 1/6, or do you have some theoretical way to explain this 1/6 power law?
Oh, this results for 1/6 and 1/4 is because the energy distribution, and because this causes this relation, and is a lower value comparing with a sphere or impacting on the granular substrate. And we obtained for our experiment 1/6, and we observed for literature that the factors that they obtained was nearly to 1/4 and the 1/5, and we just can want to show you that this factor is different for each type of sand and each type of liquid that you use for the droplet.
So you believe that this factor is dependent of the type of sand?
Yeah, for sure.
So
the type of the sand, the size of the grains.
The opposing team agree with it?
Yeah, I think that the power law would depend on several parameters, but it's not clear to me how they explicitly do depend. And I think it would be very interesting to see how that power law changes when you change the experiment parameters.
Okay,
yeah, I agree with you.
That's what I want to say. Thank you.
Claudio or Alberto?
Hi, I have 3 questions. 2 to the reporting team, Unicamp, and 1 for the opponent team. For Unicamp, explain the physical concept of Weber number to me. The second question is, what is the place that you take the sand beach? And for the UFABC, the opponent team, Reynolds number of what you are talking about?
Okay, may I answer first? The Weber number is the ratio of the inertial forces and the surface tension. And we obtained this bit sand from Fortaleza.
Regarding the Reynolds number, I was talking about the droplet, the liquid droplet Reynolds number, because the maximum reach for like a droplet falling on a hard surface instead of a granular surface like this one, the maximum reach does depend on the Reynolds number and also the Weber number. So it's a combination of both.
Thank you to both.
Okay, Claudia.
Okay, I couldn't hold myself to comment that you got a nice send from Fortaleza, my hometown. Okay, now to the question to the presenting team. Where did you get your velocity? Did you get it from energy conservation from the height, or did you measure the velocity through tracker or something?
No, yes, I obtained from energy conservation.
Okay, what's the typical size of your small droplets? What's the typical diameter from your
typical
needle?
Diameter of the droplets?
Yeah, approximately.
We obtained it from a relation from the diameter of the syringe and the surface tension of the rotor, and it was about 4.4 millimeters.
4.4 millimeters. Okay, thank you.
Yes. Thank you.
For the clarification. Okay.
Okay, Alexandre.
So for the reporting team, so the glass plate, is it suspended or is on the ground? And since you use a very thin layer of sand, how can you be sure or infer the effect of the glass plate or the surface that you use underneath the sand on the experiment? And where do you think it would affect, if you have any effect on the dissipation?
Oh, and the plate was on the ground, right? And we compacted it in the ground. And the effect of the thin layer of sand could be the deformation of the crater, and I think the energy will be more wasted in this process.
Actually, our main experiments were done on a thick layer of sand, just to be clear.
Yeah,
When you say thick, how thick is it?
We used for this 4.80 millimeters.
Okay.
So how did you vary the height? Oh, sorry, Alexandre, I interrupted you.
Yeah, it's okay, it's fine.
Okay. So how did you change the height? Because it was in the picture, it was a fixed height there.
Mm-hmm. Yeah, we varied in our home using places in our home, and sometimes we were peeling objects under the plate to vary the height with more controlled way.
So you changed the height of the plate and put it in books or what?
Yeah, I used books. Sometimes you vary the fix of our support in some places in our home that we can vary it. And when the distance from these places were very high and very different, we use the objects under the plate. But we compacted in the ground and transferred to the objects.
Okay. What happens if for the same height you have, what is the difference of diameters you measure? You tried it?
Yeah, but for the same height, the difference was very low. We obtained almost the same diameter of the craters.
Okay. Thank you.
Okay, one final question for the Claudio.
Okay, just looking at my notes here, my calculations to both teams. Do you expect the air drag to make a difference in this calculation of the velocity with respect to energy conservation from the height? For
Yeah,
instance, I got a for yeah. So for the typical droplets that they are using, can you comment?
We didn't measure this very well because the heights were not too high. The highest that the heights of the release droplets that we used were not too high. But we know, for example, our rain droplet, this is very important, and the droplet including achieves a terminal velocity.
I think that for any height like above half a meter, the air drag would be of considerable influence to the final velocity that the drop reaches. But for very low heights, I don't think it would be of significance.
Just as a reference, I just did a fast calculation here based on a paper on terminal velocities, and for a 4.4 millimeter diameter droplet, the height would be 4 meters for reaching a terminal velocity. So you are at the maximum height of 1 meter. So I don't know. Maybe there is some influence.
Yeah, okay. I think the droplet don't deforms too much in our heights that we used, but it's an important factor to consider.
Thanks.
Okay, thank you, everyone. Now the jury has 1 minute to decide the grades. Okay, I have the grades now. I will start with the grades from UFABC team. So, Alberto, 10. Alexandre, 7. Claudio, 6. Ubirajara, 6. Ian, 5. Alberto, I think now I'm saying it again.
Sorry,
No, I think that's wrong. I think you read the last one.
Yeah.
Yeah.
The last grade, I confused?
I think so.
Yeah, the last
I think you're reading for the first round.
For the first round, not the second.
For the first round? Okay. Okay, so let's consider what I said. So Alberto, 10, right? Okay. Ian, 5.
Unicamp or UFABC?
This is for Unicamp now. Okay. Sorry for the confusion.
Again?
Ubirajara, 8. Alexandre, 9. And Claudio, 9. Now for UFABC. For Alberto, 10. Ian, 5. Ubirajara, 8. Alexandre, 9. And Claudio, 10. Okay. Yeah, you can.
I would like just to comment my grade. In fact, I recognize a hard effort of the Unicamp team in doing the experiment, and I know that you have worked hard, but I really don't agree that you had solved the problem. In fact, this power law, it's kind of already established in literature, and is 1/4, and it does not depend on the sand. In fact, you have just 10. I think that you have a problem in your measurement, because you have measured, the crater, not the external, but the internal one, that was a little difficult to determine which is the greatest failure. We can talk about later if you want to see these articles that propose a theoretical explanation. But in fact, I congratulate you for your work, and if you want to talk later about these points, I would be glad.
Yeah, I'd like to congratulate the Unicamp team for the very nice experimental setup. And I think you can get a little bit more data there to really make this a very, very nice study. Also statistics, as the other team suggested, and also take into account this drag force to see if there is an effect, at least order of magnitude calculation. Maybe it's only a 5% effect, but it will affect as the height grows. So maybe it's worthwhile taking this into account. Okay, right. And the other team went into the points, I think, that are main points. So congratulations to both teams.
Alberto, you can continue.
Congratulations to both teams to the way that you presented, the people presented from Unicamp. I like the literature, the way that you collect the data. So I'm really pleased to see your presentation, and I'm also very happy to see how the guys from UFABC questioning you. Congratulations too for your way that you talk with them. And I just like to say to João Pedro, it's not a negative criticism. It's just saying that the way that you answered me about the Weber number is not correct. You can see the recording in some places of your answer, but based on the formula that you presented, and you have also showed that Weber number is related to velocity, and somehow is related to velocity. So questions like this drag or things like this is everything is answered inside the Weber number, and that is not just surface tension and viscosity, things like this. And the Reynolds number, people from UFABC, Reynolds number talks about things about a continuous line flow transition to from laminar to turbulent regimes. So when you see a drop falling, you are talking about the Reynolds number of what? Of the air around the drop, of the water when it impacts the sand. So be careful when you just ask this type of things, that you have to know what the concept is behind. The physical concept is important. It's not just quantitative measures. You have to understand what you are doing. But I was very impressed with your work. Thank you very much.
Alexandre?
Yeah, so I would just like to say that this was probably the best fight I've seen so far. It started off with a very nice presentation by the Unicamp team. Again, the best presentation. I've been following them since the first day, and this is the best presentation they've done so far. The experiment was very nicely carried out. They did a very nice introduction, which I criticized on one of their fights before. And also, I mean, they put out, so there was an experiment, there was an introduction, and there was some theory, there was some nice physical law behind it. So they, everything kind of connected. And I mean, the cherry on the cake is the fact that the UFABC team there did a very nice discussion. So I think both teams completed themselves. And so you're both very, did very, very nice job, and I think it was a very good, nice fight. So congratulations to everybody.
So thank you, everyone. Good luck for the teams in this afternoon. So I will stop sharing, and bye-bye.
Thank you, everyone. Very nice fight.
Recording stopped.
Thank you, everyone.
Well, jury and the opponent team. Se você quiser conversar um pouco do que você tinha falado, não sei se é agora ou mais tarde.
Então, vamos depois da competição, né? Aí depois a gente
podemos, sim.
Né? Com quem ganhar a competição, a gente conversa um pouquinho sobre os problemas. Com certeza, se vocês ganharem, a gente vai marcar uma reunião.
Com certeza.
Com todo mundo.
Mas eu não vou te
com
falar
todo
nada
mundo,
agora,
com
né?
certeza.
Todo mundo.
Mas se eu falasse algo, eu não ia mudar de hoje para amanhã, não.
Tarde. De agora, né? Mas,
de agora para tarde.
Só para não te ajudar no final lá. Mas beleza, boa sorte aí para você.
Legal, obrigado, gente.
Pessoal, só falando aqui então para lembrar vocês, 12h15 mais ou menos os capitães para a gente decidir os problemas, tá? Eu vou calcular as notas agora de todo mundo e aí 12h15 eu vou pedir para os capitães entrarem na sala A para a gente ver qual vai ser os problemas, porque na final, vocês sabem, não tem desafio, né? Vai ser só cada um apresentando o problema, beleza? Então, pro pessoal do YouTube aí, tchau, tô fechando a transmissão aí, a gente se vê à tarde, às 14 horas na final.
Até mais, pessoal, até a tarde.
Até mais, pessoal, até de tarde.
Tchau, pessoal.
Boa tarde.
Excelente.